chapter is hash tables. And let me try and make sure this is in the part of the screen that's being captured by the streaming. All right, so hash tables are a real important data structure. Now, arrays and lists are previous. So arrays would just have an index number here storing data, and you have items 0, item 1, item 2. That's arrays and lists. They both index them by have an index number. And hash tables use something other than an index number. So instead of just putting them in one after another, you put them in as key value pairs, like dictionaries. And dictionaries are in fact often built using hash tables. And the point of this is data retrieval can be very fast. So you have a dictionary. Here we define a dictionary with Besant is the key, and the value is this number starting with 982, and RCAM and this value. And there are 4 people with these numbers and those values stored in the database. And all right. And here you fetch one of them, myDict, and you use the key, RAM, as the value to search for, and it'll find the number matching RAM. So that's a dictionary, and we've used them before. You have keys, and you have values, and it's key : value to separate these items. So that's one way to do it. Now, a hash table works like this. You have the keyword, and you reduce it to a hash, which is a number, and then you find the value from that. And here, the hash function is to convert each letter to numbers by the ASCII chart, add them up, modulus 256, so it's 1 byte, and you get one number from 0 to 255 to represent any string of any length. So here's the code that does that. Here's the loop. You have the name here, and for C in name, you just add the ord of C. The ord is the integer ASCII number for the character, and then you add them all up, and then you take it modulus 256. That's how you make this particular one. Let me check for comments in the Twitch. No new ones. Okay? All right. So you have to have a hashing function. You have to have some way that you feed in your data, which can be of any size, and it somehow gets boiled down to a function, typically fixed size. So here's a hash function. This is sum of map of ord. That's another way in Python to accomplish the same thing. It's going to take all the letters, hello, space, world, turn them all into ASCII numbers, and then add them up and get the total. Now, the hash function we used before would take this modulus something. This one just takes the total, so it will be bigger for longer words. So here's 2 strings with the same hash value. If you take hello world and you move this back one in the alphabet to G, and you move this forward one to X, then this 104 turns into 103, and this W turns into 120, so the total is the same. So now you have 2 different strings with the same hash value, and that's called a hash collision, when you have 2 different inputs but they hash to the same value. And hash collisions are a problem for hash tables and hash functions in general. A perfect hashing function would create a unique hash value for any input. And if you use a modern hash function used for general purpose like SHA-2 or SHA-3, it's effectively having this property. In principle, there are collisions, but in fact they are so rare that nobody has ever found any of them yet. So they approximately have this, but perfection makes the hash function slow. So what you actually do is you use a fast hash function and you let it have collisions, and then you have a strategy to resolve the collisions. So one way to do it is to add a multiplier. So instead of just taking each letter's number and adding it up, you can multiply it by a number which represents its position. So this is multiplied by 1 and 2 and 3 and so on. So now you get a bigger number. But now if you change it to Jello Zorl, it'll of course be a different number, because changing this character by 1 changes the output by 7, changing this one will change the output by 1, so this is going to be a different total. So this does stop that collision, but of course there will be other collisions that will happen. For example, you could move the E down by 1 and the H up by 2, and that would make another collision. So to resolve collisions, first you need a hash function that has them. So if we'll do the same thing, we'll do the sum of the ASCII values, and then we'll take it modulus 256. So now hello world is 92, and eggs is 51, and data is 6. So this is a hash function you can use, but of course it won't be too hard to find collisions in that one. So to resolve collisions, hello world and world hello will collide. They're both going to have the same total because we didn't use a multiplier to represent the order of the letters in any way. So there are ways to resolve these collisions. And what you do is when you try to store data and you find out that hash value has already been used, then you have algorithms to try a different hash value. And there's linear, quadratic, and double hashing are three possible methods of finding another hash value. So linear probing is simple. You try to store the data here, but it's already in use, so you just move forward. Try adding 1, adding 2, adding 3, just add to the hash value until you find an open space. So this one, that's the idea. Repeat until you find the next free space. That's linear probing. Now the problem is you might accumulate clusters of items. You might, because you're just in order, then you might have a collision at the first one, that fills up 2. Now if either one of them has a collision, you fill up number 3. Now if any one of those 3 have a collision, you fill up number 4. So it's fairly likely that as your hash value approaches being full, that you're going to have blocks of contiguous filled items, so you'll waste a lot of time hopping through there hunting for things. This may create dense areas where other parts remain empty, and that will make your hash table inefficient. So that's one way to do it. Here's one way to implement it. You define a hash item, which has just got a key and a value. And here you define a hash table, which has room for 255 items. 256, I'm not sure, maybe, why you make 256 instead of 255? Oh, 0 to 255 probably. Yeah, that's fine. So there's your hash table. It will store data with a hash value. And now you have a hash function. If you have an internal function you don't want to expose to the end user in the library, you put an underscore in front of it. So this is the hash function, which is not expected for the end user to use directly. And here's the hash function we've been using. You take the ASCII value of each character and multiply it by a multiplier that starts at 1 and goes up for each character. So this is implementing the one we saw a few slides ago. This hash function is this one, where you have the 1, 2, 3, 4, 5, 6, 7, 8. But I think you then make it modulus 256. Yep, self-size. So you have the multiplier, so the position is included as well as the value, but then you modulus it 256. So the output is guaranteed to be between 0 and 255. All right, so now you can store elements. Here's a put function that will do it. This will just find, it will add it there, but if it'll only add it there if the, let's see, so here we have the hash, we have a hash item, self-hash key. I know what it's supposed to do. I'm not quite sure I understand how to read this code. Oh, while the slots are not equal to none. Okay, this is the linear probing. While it can't find it, it's going to take h equal h plus 1% self-size. This is the part where it goes forward, hopping through the table, hunting for an empty space. And then it goes down here and sets that item to the item. So that's the game. And then it'll call check growth. Growth will decide if the hash function is so full that you need to make if the hash table is so full that you need to make a bigger hash table. So you can grow it. This one decides to grow when it gets 65% full. And then it will decide to grow. And that's called the load factor, the use slots over total slots in the hash table. So here's the check growth. It will, if the load factor is greater than the max load factor, then it will print load factor before growing the hash table. Then it will perform a growth operation and print what it changes to. And the simple way to grow it is to just double the size. Table is twice the size. All right. And then it inserts all the old values in the new table that's twice the size. Now, one thing that ought to happen, I'm not sure they included that here, is you ought to somehow change the hash function so it has hash values that go up to the larger value now. Otherwise, you're not gaining much out of this. So that's the game. All right. So if you're going to retrieve elements, you have a key value like a word. First, you calculate the hash. Then you look up data at that hash value, which is order 1, because the hash value is a nice linear plan. You made a table of slots from 0 to 255, so it's an array. You just go to that location and find the data. And if you find the data, you're done. Otherwise, you have to keep adding 1 repeatedly until the desired key is found. So you look here, but the key does not match, so you go to the next one. Now the key matches. But this makes it really fast to look things up because you were able to calculate the location from the hash value and go right there. You didn't have to go hunting through the list to find it. So here's the function that does that. It will look to see if the key it found in the table equals the key you fed in. And if it does, then you're done. Otherwise, you have to go up by 1 and try again. All right, so you can implement it as a dictionary. We've been using put and get. But here we can just use hash table of good for get. That's how it works. And you can use set item and get item. These underscores means these are not intended for end users to use, but they are attributes that play in dictionaries. You can we're going to define them here. So we're going to define set item to put and get item to get. And so now we have, we assign it with HT of good. Eggs, ham, spam do not collide. Here's a bunch of them going, AD and go. And there's the, for key, we calculate the hash table and print the value. So let's see what we get. We should have here's the output. So here's the elements, and the number of elements is 5. 1, 2, 3. I wonder if none is one that doesn't count. I think that's right. We only put 5 things in a table: good, better, best, AD, and go. And here we printed out the entire hash table. And the hash table has a total of 5 elements, full, and 1 in the middle, none, that's not used yet. That's the idea, making a very small hash table as a demonstration. So that's linear probing. And the defect is you might get a whole bunch of a block of filled locations, so it makes your table inefficient. So the alternative is quadratic probing, where instead of just adding 1, you try adding 1, then 4, then 9, then 16. So you space it out more. And so if you make a very simple hash function that only goes up to 6, 0 to 6, then you can see how it goes. So you put in data at hash number 1, hash number, and then you add this one, which has a collision. So it adds 1 to get the new item. Then you add another thing that collides, and 1 is full, so it will go to adding 4, and so on. That's quadratic probing, to try to avoid making a block of contiguous used hash values. So this suffers from secondary clustering, of course. If you keep having the same primary hash value, you'll keep trying to add to here, and that sequence will go, so it can have a similar problem. All right, and you only have to change a few things to do this quadratic probing. Here's where you add the square of an index instead of just adding an index when going to the next site. That's essentially all you have to do. So another way to do it is double hashing. So you have a second hashing function. When a collision occurs, use the other hash function to get a new location. So we're calling this H superscript 1 and H superscript 2. You combine the first hash and you add the second hash value with some counting number here. So that determines the step size, and you jump through integrals, multiples of that. So the second hash function should be simple and easy to compute, never result in 0, and be different from the first one. That's the idea. So here's a possible second hash function. You take a prime number minus the key mod prime number. So it's just a way to quickly get another number, which will be different for each value of the key. And so now you have the first one hits, and you add another element. You get the other hash tells you to add 3. The other hash is 3, so you add 3. Next time you add another value that has the same original hash function, but since the key is different, the second hash function will have a different value, like 1, and you put it there. So now you're not going to have this problem where if you have multiple collisions on the same spot, these all pile up in the same location, they'll get spread out. So that's another way to do it. All right. And all right. And the code is pretty obvious. And here you have, instead of h plus j for linear, or h plus j times j for quadratic, you have h plus j times the other hash function, which is prime number minus key times key percent prime number. All right, and then there's another way to handle collisions, where each slot in the hash table stores not a value, but it stores a pointer to a list. And now you just have a list of items stored there. So this is another way to do it. And then if the table gets full, of course, then you'll spend, even though it's very quick to do a hash and find the hash value, you then have to read through a list. And if the hash table gets full, the list will grow proportional to n. So this is going to have order of n if your list search becomes a significant time waster. All right. And so they say it's better to use binary search trees instead of lists, where you'd have each hash value point to a data structure, and that data structure can be a binary search tree. So now, even if you have to spend a lot of time in this structure, it's fast, it's log n instead of n. All right. So symbol tables is an example of something you store with hash functions. This is used by compilers and interpreters to keep track of things. I know I've come across them for hacking. If you make a program and you compile it like a C++ program and then distribute it, you typically strip out the symbols so it's harder for a reverse engineer. So you don't have the names of the variables or the names of the methods anymore. But when you compile it and maintain the symbol table to make it easier for the programmer to debug it, then you keep track of this stuff until you'll have literal names like Joe and ages. Name and age are the two symbols here. Name is the name of this variable, and age is the name of that variable. So those are symbols. You have all the symbols in your program are stored with hash functions of some kind. So you take them and turn them into, you specify what they are and you store them here, and typically you'd store them in a hash table. All right. So let's try a Kahoot. Let me just check and see if there are comments online. There are no new ones. All right, let's take a look at the Kahoot, which is here. No sound? There we go. Okay, good. Okay, what data structure retrieves an element like that? A, with just a alphabetical value in quotes. That's a dictionary. You've been using it for a while. Dictionaries have key values, and the keys can be anything in quotes, and you'll have a value coming from it. The keys, I think, can be numbers too, that numbers that don't need the quotes. All right. All right. So which collision handling method creates dense regions of consecutive occupied positions? That's linear probing, where you go to the next and next and next, and that's what creates the pileup. All right, which method lets you store more data items than there are possible hash values? only separate chaining. All the others just find different ways to find an unoccupied hash value, but if all the hash values are occupied, you can't store any more data unless you use separate chaining for each item points to a whole list of items. And then you can have as many as you want. You begin to lose the speed efficiency of the hash table by adding them, but you can store as much data as you want. All right, which method requires two different hash functions? That's double hashing, of course, as the name would imply. One hash function gives you the original key, and if there's a collision, you use the second hash function to determine the steps to add to the hash function to find an empty slot.